start recording. Okay, perfect. Hello, everyone, and welcome to our reading group. Today, we have a pleasure of having Minje from University of Illinois at Urbana-Champaign. He's an associate professor at Urbana-Champaign and also a visiting academic at Amazon Lab. He's working on developing machine learning models for speech and audio problems, and he has been recognized with various awards, including NSF Career Award and many other awards. So without any further ado, I want to hand over the stage to you. Stage is all yours.
Thank you, Pone. Thanks for having me. This is a really interesting series of speech, and I'm glad that I can join this party. Today, I'm going to talk about some really interesting practical issues like efficiency and scalability of machine learning models if they are used for speech enhancement. So first, I'm going to talk about some motivation why this is important, and I will try to introduce some general model compression algorithms for speech enhancement. And then I will move on to this other interesting personalization topic, which is actually a really nice way to compress the model. And we'll introduce a couple of my work on this, which is based on well-known knowledge distillation and the mixture of local experts models. And then I'll move on to this scalable and efficient model topic, and we'll introduce the other couple of papers about something called the BloomNet and the core diffusion based one. And we'll wrap up the talk with some discussion. This work was done mostly with my former students, Sunwoo Kim and Aswin Sivarman, who all graduated now. And then the last one, core diffusion one, was done at Amazon with my manager, Kirsty Christiansen. So as a motivation, let me just briefly introduce the speech enhancement problem as a benchmark task. So when we develop a speech enhancement model, it's usually done in this way. You collect a lot of speech utterances from many speakers that are all different from each other, of course. And then we also collect a lot of different noise signals as well, and they should be different from each other as well to reflect the reality. And then we add them together or to form this noisy speech, and we also maybe introduce some reverberation or other artifacts as well to again mimic the reality. And then we train a big speech enhancement model, which is parameterized by large enough parameters W here. And then finally, the output of the system, the enhanced speech, will be compared against the original clean speech we prepared during training, so that the model learns how to clean up speech for many different people and different noise sources. So given this, the typical application goals for speech enhancement is, of course, to improve the audio quality. Audio quality is, by the way, not well defined here because some people just pay more attention to the intelligibility of speech because it has to be used for, ASR backend or even for speech communication. Intelligibility is always important. But at the same time, there could be some other things like a perceptual audio quality, despite all the subjectivity of the definition of perceptual audio quality. So this is like a really traditional goal of training some machine learning based speech enhancement model. But at the same time, we also need to worry about the other things like online or real-time processing, because most of the time speech enhancement models are used for speech communication where things have to happen in real time. So if the model introduces some delay, like a long delay, such as 0.5 seconds or something like that, even if the sound is good, but it's not going to be good for speech communication because people have to wait for each other for the processed speech signals. So we need to worry about these things as well. And on top of that, we also want to use this on many different devices. So if you have to do this on device, then we, of course, need to worry about low complexity, and means that big models like this will start to matter. So basically, if you train a general purpose speech enhancement model, like I just introduced here, you dump big data set to the big model, then it works really well, actually. These days, they work amazingly well, but it is just too complex for some small devices, potentially introducing a lot of issues for real-time processing. So that's why we need to do some model compression. What is model compression? Simply put, you can just come up with a small architecture and then hope that it works well. But we all know that it doesn't work well if the model is too small. The other more clever way would be, you start from a big model, But instead of just making the model smaller by reducing the number of layers or hidden units, you just, for example, come up with some strategy to prune some weights because some weights are not really contributing to the sound quality. So that would be another sort of a more advanced way to compress the model. Or, if all the model parameters are stored with this, single precision floating point, that could be maybe waste of computation and space. So, you can produce some low bit quantization, using only fixed number of bits to represent all the model parameters. That would be actually much better for some hardware because hardware prefer low bit precision. So that's some, like a typical ways to, do model compression. But today I really would like to introduce some like interesting like perspectives to this. Something based on speaker agnostic model compression. I mean, speaker actually dependent model compression. So if the model knows about this target speaker, then maybe we can do something better than speaker agnostic model compression that we just saw here. Or we also need to worry about scalability, which I'm gonna elaborate a little more because just simply coming up with a small model might not be always the best idea. So there are a lot of ways to compress the model here, but as a like starter, let me introduce this low bit quantization approach that I have worked a lot on in the past. So, just to give you some background about this, we all know this XOR problem, which is a non-linear problem, right? We have this, circles here and the crosses over there. So there's no linearly separable, hyperplane that can classify these classes into, circles and crosses. So we always need some, at least a couple of, linear decision boundaries or non-linear decision boundary, right? So if you think about the solution here, there might be many, many different decision boundaries that are combined together to solve this, non-linear classification problem. But what's really interesting here is that there's a binary solution here. If like this particular solution, for example, happens to be the perfect solution, I would say, for some reason, this is a maximum margin solution of this classification problem. And if you sort of represent this as a neural network, then you can see that all the network parameters are all plus ones and minus ones. So you can actually use one bit to represent this model parameters. And it sort of sometimes works really well magically. Because most of the time you don't need that much precision to do the inference. So this is of course there are slightly different versions of this, such as using 3 bits instead of 1 bit, or 8 bits, which is much better. So something low precision would really help the hardware inference time and the inference time complexity. At the same time, they are capable of solving nonlinear problems, although of course the performance wouldn't be as good. And this is like a really quick, sort of comparison between the binarized network and the original floating point network. We see that if you reduce the bit depth to 16 bits and you represent the model parameters using fixed points, then you get this amount of compression in space and power consumption. But if you also introduce additional bit depth low quantization model like a binarization, then this is like amazingly low complexity model. So, we can just consider this because it's very important. So I went ahead and trained a binarized bitwise neural network for supervised vision denoising, and this is the performance. These SDR, SIR, SIR, or they are all sort of a variations of SNR measures, so the higher the better. And you can see here, binarized network is almost as good as the non-binary network for this particular architecture, for this particular data set. So the zero point 0.5 decibel difference here is like a barely audible difference if you imagine, if you don't know about this metric. And what's also interesting here is that in some other metrics, like STOI, speech intelligibility scores, actually binaries network is a little better. I'm not going to argue that binaries network is better always, but it's just that saying that we can do a lot of compression by lowering the bit depth of the model parameters. So let me just actually check on the performance over here. Can you, how about
We
this one?
always thought we would die with our boots on.
This is the input noisy speech.
We always thought we would die with our boots on.
And this is the processed one.
We always thought we would die with our boots on. We always thought we would die with our boots on. We always thought we would die with our boots on. We always thought we would die with our boots on.
Can you tell the difference between these two? You don't have to answer me because it's over Zoom, but actually the left one is like a proper neural network, and the right one is bitwise version, although the first one is actually using the binarized input, so it's a little unfair. But anyway, as you can see here, the difference is kind of barely over this Zoom, apps compression algorithm and whatever funky things happening in between my computer and your computer. But normally, if you listen to the signal really carefully with some, expensive headphones, then you can, of course, hear the difference, but, it might be just over. And then, by the way, the models I'm showing here, they're, based on fully connected network, which is so boring. So I attempted to binarize the GRU models, and it's actually doing something similar. As you can see here, the GRU model with no sense of quantization or anything, it does this kind of speech enhancement. And after binarization, it's doing something like that. So if you look into these spectrograms after processing, you see some difference here and there. But when you listen to the signal, they're actually pretty good.
She had your dark suit and greasy washwater all year. She had your dark suit and greasy washwater all year. She had your dark suit and greasy washwater all year.
If you listen to them really, really carefully, then the binarized network is a little worse. So actually, the SNR number is a little worse as well. But if you have to run this on a very, very, very small devices like hearing aids or AirPods or small things like that, actually this would be a suitable solution to that problem. So finally, I know everybody's really excited about deep learning based speech enhancement, but let me actually switch gears a little and then introduce a hashing based approach, which is a really fun thing to do as well. So you start from this mixture spectrum, which is again speech plus noise thing. So if you look at this spectrum, you see that the black spectrum is for speech, and there's a noise over here. And of course, the model doesn't know this color. So if the model fits this spectrum, then it's just a mixture of these two. And then eventually, if you can come up with this kind of mask, which will sort of suppress this noise part, your job is done. So uh, imagine that we have like a large dictionary of all the masks, like this orange one. And then, the speech enhancement job would be to find out the nice mask from this dictionary. And then, of course, there can be multiple, good mask solutions. And then you sort of average them out and then mask the input signal with the mask. Then you're going to do nice speech enhancement. So it's really like, finding out the best matching mask vector from this that's associated with the mixture spectrum. And we can sort of set this problem in this way by coming up with a mixture spectra dictionary from the training data. So we, combine a lot of, clean speech and noise sources and so on, and then come up with a big dictionary. And then since we did it during the training time, we can easily infer the ground truth mask vector dictionary as well. So somehow, if you succeed to find out the matching most similar mixture spectra from the dictionary and then corresponding mask, then your job is done. The thing is, this search will take a lot of time because the dictionary is really, really large. So we can sort of introduce some fancy hashing algorithm to convert this input mixture into bit string. And then we also convert all the mixture spectra dictionary into some hash code, binary hash code as well. Then the k-nearest search on the hash code will be instant because we can use bitwise operation. So that, that will do the similar kind of speech enhancement because the corresponding mask can be also found by using the index. So hashing can speed up the search. Everybody's using for, information retrieval these days or database. And because search is based on the bitwise Hamming dissimilarity. But hashing can degrade the performance because the Hamming dissimilarity isn't guaranteed to be similar to the perceptual similarity as well. So we need to be worried about it. And then, of course, we need some machine learning there. I'm not going to introduce this algorithm, but we worked on some other boost algorithm that works with the locality sensitive hashing to resolve this issue. So if you are interested in this kind of thing, you can read our paper. But long story short, I would say I pretended like, low bit solution, low bit quantization of the model can compress the model without the loss of performance. But the truth is that actually in a lot of cases, if you compress the model too much, especially for some particular architectures, you see a lot of degradation. So I'm going to move on to this next topic, which is personalized speech enhancement. This might sound like just use speech enhancement algorithm, but it's actually really good at compressing the models. So let me introduce the motivation behind this. So there can be a generalist speech enhancement model, which is working really well universally for any speech or mixture of speech or noise sources. For example, we could have some speaker A whose speech is contaminated by some dog barking, and then the model has to clean it up and then recover the user A's clean speech accordingly. And then for the other user who's contaminated by some drone propeller sound. Again, it should work well. For the bird song sound, it should also work well. So this model just has to work for any combination of noise and speech. But what if there are some specialist models that are specialized for the speaker or the noise? And what if that problem is actually simpler in that way, and we don't need a big model to solve that simpler problem? There was some idea behind this. Let me actually show you some results here first, because it's sort of fun to listen to. So suppose that there is a speech plus bird singing sound here.
Are you looking for employment? Are you looking for employment?
If you happen to choose the best specialist that's trained to solve this problem really, really well, and it's very small, by the way.
Are you looking for employment?
You can do speech enhancement. But if you choose some wrong specialist that doesn't know anything about bird singing or the speaker, then it's gonna sound like this.
Are you looking for employment? Are you looking for employment? Are you looking for employment?
So it's sort of obvious that if you train a specialist model for the particular test and problem, then it works better than the generalist model, especially both have to be small. But how do you actually train a personalized speech enhancement system, especially if you want to, personalize the model for that target speaker? Because usually we don't have access to the clean personal speech of that test time user. We don't even know him or her who's going to use this kind of system ahead of time. So there's like a chicken and egg problem. One way to solve this problem is by using knowledge distillation for personalization. So this is based on the assumption that there is a large teacher model who knows about everything, who is good at all sorts of speech enhancement problem. He can solve this, problem really, really well. The only thing is that, he's a little too big, too expensive. Salary is too high, too higher. So maybe it's not a good idea to use this for the small device. And there can be a pre-trained small student model. Since it's a student model, it's small and efficient and cheaper to run because it's small. The only thing is that the performance is not good enough because it's a student and it can make some mistakes. And at the same time, students doesn't know how to fix the problem because there is a lack of ground truth clean speech. Again, we are talking about specializing the student model for the particular talker who we don't know yet. So during the test time, what we can do is we can sort of adapt the student model to that test time speaker so that the student model works better on that particular situation, which can be done by, knowledge distillation. First, we feed the test time noise utterance, and then we feed it to the teacher model and hope that the teacher model works really well for this test time noise utterance. The only thing is that, this is not going to be the ground truth clean speech because teacher pretends like he knows about everything, but he actually doesn't know about everything. So it's just the best effort result from the teacher model. Now, we're going to feed the same test time noise utterance to the student model, and the student model will do his or her best, and it's going to come up with some solution. And then we can set up some loss function and then do some fine tuning on the student model. But in this case, we are using the teacher model's output as the pseudo target and then do fine tuning. So of course, the assumption here is that the teachers are better than the students. And I hope really this is the case, meaning that if we had access to the ground truth clean speech, and then compare the loss between the teacher's output and the ground speech, and then the student output to the ground truth speech, then the loss here is lower, meaning that the teacher is doing a better job, meaning that the student has to learn from some better teacher than the student, right? So that's sort of the fundamental assumption, and it usually works well. So the use case scenario will be something like this. The student model will be the only model that's used during the inference on the device. So device only has the student model, for example. But if the student model needs to be updated, then what we can do is we can sort of fine tune the model. But fine tuning can happen in, for example, in the cloud by having this copy of student and teacher model in some cloud server. So during the device idle time, student model can be updated over the air because the cloud copy after this knowledge distillation can improve the performance. So this is sort of the overview of the system. And the rationale behind this idea is that you can think of this problem as from the manifold learning perspective. So you suppose you have this clean speech manifold of everyone, all the speakers in English, then this will be a very, very complicated manifold, and it's going to be difficult to model. Suppose that you start from some noisy speech utterance, then what your model is supposed to do, the student model is supposed to do is to convert this noisy utterance map it onto the manifold of the ground truth clean speech. The thing is, the student model is not good. It's like a small model. It's not capable of modeling this complex mapping. So the result will be sort of a smoother manifold sum average that happened, which is not as good as the original manifold. So it's not a good idea. However, if you think about the personalization idea, meaning that if you can somehow sort of set aside some interesting speakers for the target talker, and then ignore all the other speakers from the problem space, then the problem reduces down to this smaller subset, and hopefully the manifold of that clean speech of that similar speakers for the single talker will be much smoother than the original. What that means is that if the student model is trained to estimate this smoother clean speech manifold, then it might be able to do the job. That's sort of the idea behind this. The reason why we hope that the personalization can help the model reduce its size. The thing is, we don't have access to this clean speech of the target talker because we are talking about the test time speaker, which we don't know yet. So that's why we need to use some teacher model, which is good on this manifold mapping problem really well anyway. So we're gonna learn this yellow manifold from this teacher model, hope that this yellow manifold is similar to the target talker's manifold. And then finally, we use this yellow manifold as a target of training, and then train the student model accordingly. And this can do the job. That's basically the idea behind this. If you look at the results, it's really interesting. So the yellow and the blue boxes are all the fine-tuned, distilled student models. And you can see that they are actually better than the corresponding gray boxes. By the way, the x-axis is the complexity of the model. And as you can see here, the teacher model is the most complex one. And they're like a varying degree of complexity of the student models. So all the yellow boxes and blue boxes are better than the gray boxes. Great. The other thing is that the other interesting thing is that if you look at the smaller model architecture for the student model, you will see that the performance improvement by doing this knowledge distillation and adaptation is much bigger than the same situation for the larger student model. So larger student models who are already doing well, maybe 70-year PhD students, they don't need to learn anything from the teacher. They can graduate. But for the master students, first year students, they can actually learn from the teacher because their capacity is kind of small. I know it's like not a good metaphor. Hopefully it's not deserving. But this is basically the situation. And at the same time, we can also think about this, the different teacher models. There can be some better teacher, there can be some, not so great teacher. If the teacher is better, like this one, then the corresponding students who learned from this better teacher improve his performance, the blue ones. Then the yellow teachers who didn't learn from the better teacher, but the, suboptimal teachers. So teachers' performance is also important, as we can easily expect. Um, how about the compression side? If you compare this student model after fine-tuning, and if you to the more complex model over here, you'll see that the performance is sort of on par. It means that after the fine-tuning of the student models using this knowledge translation, since the performance is better, but we didn't actually change the model architecture. So this can be seen as that we can say in this way. A small model after fine-tuning is as good as a student model, which didn't go through any fine-tuning, but its architecture is big. It means that we did some model compression. If you compare the number of parameters of this small one and the large one, and number of meg operations, you'll see that it's like a lot, like super big model compression and achieve a high efficiency that the student model can achieve. So this is like one algorithm that we came up with. It's something called the test time model adaptation, because the student model actually adapts to the situation by learning from the teacher. The other adaptation we came up with is something called the test time model selection. So this is a little different in terms of the amount of adaptation that the student the speech enhancement model does, but it's also very interesting architecture. So in this case, we actually divide the speech enhancement problem space into maybe multiple exclusive subsets. And the grouping can be done in many different ways. For example, we tried all the problem space can be divided based on the noise level. So if the input signal is too noisy, then it's group one. If the input signal is like really already clean, then it's going to be class 3. Somewhere in between, that's class 2. That can be one legitimate way to divide the space. But in this particular case, we did some speaker grouping because we were really curious about the personalization issue. So how do we actually divide the problem, like speaker groups? How do we cluster the speakers into speaker groups? Where we need to do some clustering then, but we didn't want to do it in the raw signal space because we all know that it doesn't work. So, but we found that if the clustering is done correctly, then it's going to, the assumption here is that each cluster contains speakers that are sounding similar to each other. So hopefully a model that's really specialized for that speaker group works really well for that speaker group. That was the idea behind this. And as you can see here, for example, if we cluster the data set into 2 groups, then roughly it corresponds to the gender of the speakers. So it means that as we expect, maybe it's based on the pitch of the utterances, right? If we cluster using like 10 groups, we have no idea what they mean. Maybe it's based on accent or something else, but anyway, it's going to be something meaningful, hopefully. How do we actually do the clustering? Well, it's based on contrastive learning for noise robust speaker embedding. So basically, we came up with a RNN-based speaker encoder that takes some noisy speech signal, by the way, because this one has to be robust to the noise. And then the encoder will turn this into some embedding Z sub I. And then we feed some another utterance, XJ, and then use the same encoder to turn this into Z sub J. And of course, we're using the same encoder here, just the input utterances are different from each other. And then once this is done, we compare Z sub I and Z sub J, the embedding representations of the 2 utterances. And we train it in the way that if both utterances are from the same speaker, then it's the positive class. If both utterances are if they are from the different speakers, then it's a negative class. It's we can sort of set up some logistic regression problem and then solve this problem. It's a very standard contrast learning setup. But once this is done, we can actually do some k-means clustering on this low-dimensional embedding space, which is the result as you see here in this map. So once this clustering is done, what we can do is now during the test time, we're going to feed the noisy speech to this gating module, which is basically like a classifier. And it consists of this encoder, which is the Siemens network you just saw, and then softmax on top of that, that basically does some speaker clustering classification into k different clusters. K here is the number of speaker groups. And once this is done, what we can do now is we could prepare capital K different group-specific speech enhancement models. Of course, each of which is dedicated to the particular speaker group. It doesn't have to be large. It's still solving the problem pretty nicely because the problem is much simpler. And then, during the test time again, the noisy speech was fed first to the gating module, and the gating module will make a classification decision. And then it will say that, based on your speech characteristics, you should belong to this, small k speaker group, and then activate this corresponding specialist instead of using the other specialists at all. So the other specialists are not used at all. And then you feed the noisy speech to the k specialist, and then this will give you some personalized speech enhancement result. This is a little different from the mixture of local expert setup, which is used a lot these days, in the sense that we actually exclusively use the only one local expert instead of actually blending the result later on by using the softmax. So actually, this softmax classification result will be sort of quantized by using some Gumbel softmax or soft-to-hard quantization algorithm, so that we are actually making the exclusive decision and then use the corresponding specialist only. That's how we can actually reduce the inference time complexity, because we don't have to run all the specialists. What's another interesting thing here is that, all these classification and specialist models are pre-trained, but actually after that pre-training, we can fine-tune all these specialist and classification models, because that way we can sort of let the classifier know that it shouldn't be really based on the embedding space, but based on the speech enhancement quality. So try to do some better classification. That's one instruction we can give additionally to the gating module. And then at the same time, the speaker groups can work really well, because instead of pre-trained specialist, we can use some specialist who is robust to the classifier's misclassification. So this specialist can sometimes see K plus 1 group input accidentally because of misclassification, and specialist, after fine-tuning, becomes robust to that kind of a misclassification. So that was sort of the idea behind this. If you see the result, it's sort of, interesting, and, it's as expected. So first we can see that the baseline model, it's a generalist GRU model, and we vary the model complexity from something really simple to a larger one, and the performance, keeps increasing. But at the same time, if you specialize the small GRU models accordingly, then as you can see here, the specialized or personalized models are always better than the baseline models, which is very nice. Another interesting thing here is that the index here, like from 2 to 5 to k, you will see that 2, 5, k, if you increase the number of groups, the specialist model becomes more special, and it improves the performance a little better. So that's also very nice, although there's of course a limitation. You don't want to increase the number of groups by too much. And then fine-tuning, if you compare the thin lines and the thick lines, the thick lines are always better than the thin lines, corresponding thin lines. It means that the fine-tuning lifts the performance in all cases. If you compare this particular specialist, the really smallest one, and the corresponding generalist one, we see that the performance is on par in terms of SI, SDR, But if you compare the model size, it's like 95% reduction. There's a lot of complex reduction without harming the quality of speech enhancement. And we still need to carry around all the capital K different specialists on our hardware, although we don't use them all the time. But spatial complexity is a little higher than the computational inference complexity, but still it's 50% reduction compared to the large model that doesn't do any such model selection. So let me move on to the final topic, which is about scalable and efficient speech enhancement. So what is scalability? We talked a lot about efficiency today, so I'm sure that hopefully I convinced you that efficient models are important and there are interesting ways to compress the model by using, personalization or, model quantization or whatnot. But what is scalability here? So let me use the video coding as an example. Suppose you're watching some Netflix video Monday morning. I hope you don't do that because it's a little not nice. But anyway, say you're watching this show on Monday morning. Everything is clear. You can watch 4K, streaming because nobody's watching Netflix in the morning, Monday morning. But if you watch it Friday night, then everybody's watching Netflix. So you need to the network is packed with all the packets and so on. So the network still wants to stream the video with no buffering. So instead of using buffering, it actually lowered the bitrate of your video coding so that people still watch the television with slightly lower video quality. So all the codecs, like video codecs or audio codecs, speech codecs, they actually come with this nice scalability function so that they can kind of adapt to the network situation because codecs are used for, varying, test environment. So what if we bring this idea to this speech enhancement or any actually machine learning models where there is a trade-off between the performance and the resource usage. So suppose you're running your speech enhancement model on some small device, which is running some other important things, typically video coding. And the video codec can say that, oh, speech enhancement model, I don't like you. You're using up the resources. So why don't you actually reduce your, capacity so that I can do some better decoding? Then the speech enhancement model has to react to that and somehow reduce its model complexity adaptively based on whatever request it gets from the operating system or from the signal. So that way you can sort of still do some adequate level of speech enhancement, but how do you actually train the model in this way? Because the models are not designed to handle this kind of situation. So let me actually come up with, introduce this concept a little differently because we came up with this model called the BloomNet, and this was actually having this kind of idea behind. So there was this, imagine that there is a naive scalable speech enhancement system that consists of three different models, the smallest one and the mid-sized one and the big speech enhancement model. So during the test time, if the model is asked to improve the speech quality at best, then if it has a nice resource, then it will just run the big model. But if the resource is lacking, for example, the battery is low, and if the system is doing something else, then it's going to reduce to the small model. This is doable, and we can think of it as a scalable model. But in order to do this, we need to carry around all the different versions of the models, which is actually pretty big and bulky. And at the same time, the models do not communicate each other. They're not reusing any models or anything. It's just a waste of computation in a sense. BloomNet is based on the blockwise optimization, and we came up with more weak business models, and that are all interacting from each other, so that we can sort of use this full model if the computation is allowed. But if we don't have enough resource, then the model reduces down to the smallest model. Or if the model can afford a little more resource, then we use mid-sized version. So it can really freely, scale up and down the model size. And we train this block-based approach in this way. And it works really well for any block masking-based architecture. So BloomNet is actually the acronym of blockwise optimization of masking network. So this is good, but it's sort of missing some components like visual learning and some milestone goals. So my recent work is improving upon that, and then at the same time, I have a really nice interpretation from cold diffusion model as well. So let me just introduce that version as a final topic. So as a baseline, by the way, this is like an ordinary one-shot inference model that's learned in a supervised way. You start from the speech signal, which might be in some vector space, and then you add some noise vector to that, which will give you some noisy speech vector in the vector space. So the goal here is to train a model that moves this x vector down back to this s vector by using some very complicated neural network model, which is something called the restoration process. And we need a very complex nonlinear process. Of course, the mapping function has to be very complicated. If your model is small, then the model is subpar and the performance isn't good, meaning that the reconstruction will be far from the original clean speech because it's not good. We have a very nice interpretation, cold diffusion interpretation of this because you can think of this process, this degradation process from F to N as some sort of diffusion. So you start from clean speech and you gradually add your noise source, and then you come up with this X capital T, which is the noisiest version of the signal. It's called cold diffusion, not the regular diffusion, because the noise signal that's added to this is not the stochastic noise, it's of the noise source. So that's why it's less stochastic than the original diffusion model. That's why it's called cold diffusion. But anyway, based on this cold diffusion idea, the other people at Moore came up with this cold diffusion for speech enhancement, which is basically doing the restoration using the complex model, and then degradation back to the next step, and then another restoration to the clean speech, and then another degradation, and so on. But gradually, this restoration and degradation series of operations like this will improve the performance over and over, and eventually reaches that clean speech if you iterate this algorithm many enough times. This is good, but every time when you do this iteration, it's a best effort iteration all the time. So it's really still complex operation. And intermediate results are not guaranteed to be similar to the, like noisy versions, differently noisy versions that are on the diffusion line over here. So the model actually doesn't use this too much. So my version that I proposed last year is based on the similar idea. But this time, instead of learning some, back and forth restoration and degradation process, we just learn the restoration process that's really gradual. The restoration function learns to jump to the next step, and then the next step, and then next step, like one by one. Why do you like it? Because if you do that, then eventually this like change from this one to the next one is really gradual. So since the change is really small, we can say that it's an easier problem if you formulate this as a visual learning problem, and we don't have to use a big model to do this. So that's basically the idea. And then what's another nice thing about this is that whenever you do this training, we can rely on this other t x sub t values that are sort of a differently noisy version of the clean signal. So we can use them as sort of a milestone goals. So instead of just figuring out this non-linear mapping from the noisy signal to the clean speech in one shot, we can sort of do this more guided optimization over time. And then the intermediate results on the way are actually useful, as I can show you later. So the baseline system performance is based on this, voice bank demand standard, benchmark setup. And then it's using this DCC-RN large architecture and small architecture. And compared to the input, the pass score and the cover scores are better. Of course, it is speech enhancement. Nice. And the small model, by the way, is also doing pretty well, but cover score is not as good. If you look at the complexity of this baseline one model, it's actually much simpler than the potential cold diffusion model, which is baseline number two. Cold diffusion is really, really complex, by the way, because By the way, this number of iterations 50 is a small number compared to the regular diffusion model literature. But anyway, you just have to run this inference routine like 50 times to achieve this higher performance. So the proposed algorithm, by the way, doesn't need that many iterations. We need only 5 of them, and then we can still do better than the baseline 1. Actually, compared to baseline 2, the performance is sort of on par. But if you look at the complexity, it's only 0.58% of the original core diffusion model that ran 50 times. So that's sort of much nicer because the complexity is much lower. Another really interesting thing is that the intermediate result, this one didn't go through all the iterations just once, but we can do some speech enhancement. Let me actually show you the result over here. The unprocessed speech signals is like with this SNR, but after the processing, the SIR is a little higher. It means that it did some suppression of noise. SAR is another metric we rely on when we want to measure the artifact that the model introduces. So what this means is that the model does sort of a super gentle, still nice suppression, and it never does any voice over suppression, which is a problem when you use some too aggressive deep learning based speech enhancement model on the mixed audio. So that's some argument. And then I'm going to play this sound. It will play the sound from the end of the diffusion process, like noisiest one, to the ground truth. We will feel that the performance is like gradually getting better and better, and near the end, it's going to be almost clean. But you also want to listen to that. It doesn't have any weird musical noise or artifact that the model generates, because these models are really gentle and nice, even on the way. So we can actually use the intermediate result if that's sufficient for our application.
Today I couldn't run on it. 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 Today I couldn't run on it.
Let me play another example.
Customers for the panels include the National Trust for Scotland. Customers for the panels include the National Trust for Scotland. Customers for the panels include the National Trust for Scotland. Customers for the panels include the National Trust for Scotland. Customers for the panels include the National Trust for Scotland.
Yeah, so these are audio demos. So, just to wrap up, I tried to argue that the on-device inference is costly and we needed to compress the model somehow because efficiency matters. I showed a couple of, actually 3 different models that where I was able to compress the model by reducing the bit depth representation of the model parameters and actually the signals as well. But they're not task dependent. They're like a task agnostic model compression. And I introduced some task-aware adaptation where the model can actually adapt to the noise signal or actually the speaker of the speech enhancement system user, and then we can achieve high efficiency without losing the performance. It comes at the cost of sort of sensitivity to the domain mismatch, by the way. If your model adapts to the certain user, and then all of a sudden the user sells the device to someone else, then the model doesn't work. So that domain mismatch is actually a potential issue of this. And then I also introduced the scalable models that are sort of unexplored in the speech enhancement literature. Yeah. We have a visiting student called Riccardo Micini in my lab these days, and he's kind of the other person who's interested in this scalable speech enhancement. He has an ICAS paper this year. So if you're curious about his take on this, check out this paper. Basically, what he did was, he reduced the channels of the CNN layers. So this one is actually the white bars over here are the active CNN conv layer channels, and you'll see that if there's some large noise activity, like green line, then it needs more channels to be active and so on. It's like a really dynamic way to do this. So yeah, that's sort of something that I'm working on with him these days about this research. And we have a bunch of references. And yeah, that's it. So thanks for your attention, and please let me know if you have any questions.
Thank you, Minje, for the presentation. If you guys have any questions, please drop them in the chat or raise your hand so you can ask them directly. Okay, Mirko.
Hi, Minje. Thank you for the talk. I just have a curiosity regarding the first part of the presentation, the one where
Yeah.
you do like this aggressive quantization.
Yeah.
I'm wondering when you do that, like for your task, speech enhancement, do you see also problems with trainability, right? Training the model becomes more challenging, harder, like non-numerical instabilities or convergence issues? I'm wondering just like your experience.
Yeah. It's a good question. So, if the 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 bit depth is not this aggressive, maybe 8 bits, then you can do basically back in the days, I don't know if people called it in this way back in the days, but you can basically do quantization aware training, meaning you just actually you start from some fully trained floating point model, and then you just quantize the floating point parameters in the middle of your training so that the model is aware of that quantization error. And then the backpropagation still works because it's doing the like a pass-through algorithm, which just works well. If you lower the bit depth down to like 1 bit, it's a little different because your, -1 and +1 are now very different thing from your corresponding floating point values. My algorithm, this bitwise network, is still based on this concept because for example, long story short, if your floating point weights are positive, then I use +1. And if weights are negative, then I use -1. But in between, I had this like bunch of zeros. So it's actually doing some ternary quantization. But I found that at least for the fully connected layers, you, depending on how you set up, you have only like 10% of +1s and -1s and 90% zeros if you look at the actual values. This is like, to me, also very similar to QAT concept in the sense that it's doing based on the floating point model. But yeah, like you say, as you can imagine, it's like not stable. But for example, in my case, I had to increase the learning rate accordingly and so on. So it wasn't that bad, but I'm pretty sure that this QAT with 1 bit quantization or ternary quantization doesn't really scale up to some super large models like LLMs. So that would be yeah.
And also, I saw a recent paper from Microsoft, right, doing like a
Yeah,
binary or
yeah,
ternary
yeah, yeah, yeah,
quantization. I don't remember
yeah,
the title, but yeah.
yeah, yeah, yeah,
Then I think in terms of speed up, right?
yeah.
So you show that you have like a massive energy saving, but in terms of speed up, do you think like with modern GPUs, we are like
Uh-huh.
not really taking advantage of that, or what
I
are
don't
the
think so.
issues?
Yeah. Uh, the assumption here is that we can the GPU is not available on the device. I'm talking about some hearing aid or really small devices. So this is like inference only case, and it means that actually this binary operation should be supported by the hardware. And I kind of sort of stopped working on this a few years ago because I was really excited about this and then wrote many papers, including that hashing one. But I learned that there's no hardware that supports all my like a funky bitwise operations. So, but the assumption here is that if the device is really that serious about the model efficiency, then the device has to support that bitwise operation so that it can lower the complexity or speed on the device. So it's all based on the assumption that there is a hardware about this.
Mm-hmm.
Yeah.
Thank you.
Mm-hmm.
Thank you, Mirko. I see there are no more questions. Okay.
I think there's a question on the chat box. Is it a question or? I think it's a question. Oh, I read it up later.
there any other questions from the speaker?
Yeah, I can ask a general question, if you have time.
Sure.
Minje, so like there's a lot of work for like neural coding, right? So what is your take at the moment for like compression? Do you think that like neural codecs are kind of like getting much better than like standard traditional codecs, or like
Yeah, yeah,
I'm
yeah.
sorry if like it's like maybe it's not super related to the talk, but yeah,
No,
what's your
it is actually super related to the talk. I actually gave a similar, like a talk about neural speech and audio coding to the similar audience a few months ago.
yes,
Some people
I
might
know
remember me
very well.
from that. Yeah.
I know
So
very well.
yeah, there I didn't actually talk too much about this model compression, but yeah, I think my biggest problem with neural codecs, especially for speech communication or audio media streaming, is that the models are not really affordable on the device. If you think about MP3 codec, for example, um, we don't worry about like listening to the music using our iPhone for 7 hours or 10 hours, right? It just works. And it doesn't drain the battery because they are really optimized and runs really well on the hardware. But the neural codecs that work really well, they are pretty large and like they're getting better in terms of efficiency, but they're not really doing too much model compression, which is actually something I am working on these days as well. So yeah,
I see. I see.
yeah.
So the
I'm
models are
talking.
pretty large for like
Yeah,
device.
yeah, yeah,
I
yeah.
see. I see. I see.
I'm talking to
Okay.
this folks from Babel Lab at Cisco these days, and I don't know. I
Mm.
think it's okay to announce this. They're sort of considering organizing a challenge on neural speech and audio coding, but emphasizing the complexity and the delay of the codec a lot for the communication applications. So I think you can stay tuned about that because that could actually, sort of ignite a lot of work along that line.
All right. Thanks a lot, Minje. Yeah. Thanks for the insight and
Thank
for
you,
the great
Shyam.
talk.
Okay.
So I think, yeah, if you have any further questions later on, please feel free to shoot me an email. This is my email.
Yeah.
Or, yeah.
Thanks a lot for the amazing talk. So next week we have Jia Tongshi from CMU talking about singing voice synthesis. And looking forward to meeting you all